Good evening, everybody. I hope everyone's having a wonderful day. So before I get back to where we were last day, I just want to give you a heads up that I'm preparing the exam format for you. I'm planning to release it sometime on Friday. So that's where I'm aiming for. So just like with the midterm, I'll give you a full format for the final exam. So it'll be very detailed and hopefully help you study. But yeah, so that being said, just keep an eye out for that. I'll make sure I put a big announcement out when that comes out. Anyways, with that being said, I want to get back to multi-way search trees. So remember last day we talked about the concept of a multi-way search tree. This is where instead of just having one record in a node, we may have potentially many records in a node, and we may have multiple children. So kind of like our rooted trees, much more general ones earlier on in the course, but we have a specialized structure with how we have the leaf nodes organized. And we're starting talking about some algorithms that we could use to perform operations on the multi-way search tree, akin to the ones that we've seen for the binary search trees. So, before I proceed, I just want to remind you, we talked about searching, getting the smallest, inserting. We haven't yet talked about the successor or removal. Sorry, I'm just getting very excited here. So, the big thing is that it's going to be very similar to the way it's done with a binary search tree to compute the successor. So do you recall that when we had more complicated removals that occurred, we went and got the successor of my record. I copied that into the appropriate spot that I deleted into the appropriate node where it was originally to maintain some property. In that case, it was the binary search tree property. We can do the same idea here, except there's one extra case. The main one, namely being that my nodes may have multiple records in them. So the one natural one that we've seen before was I just simply see if I have an internal node that's my immediate child, in our case to the right, and I see, is that as an internal node, then most certainly I can compute smallest on it, and I can just simply figure out what the successor is that way. That's one nice simple way of doing it. This is actually just the first case here. So this is one thing you could do to find the successor. Now, if you fail to find a child that fits into this role, it may be the case that you have multiple records. Say one that's immediately after yours. So you know that the child that is to the right, which we normally will associate with that data, that immediate one, if there's nothing there, then the great thing is because it has multiple records in it, to my immediate right will be the successor. Why? Because of the properties we have for our multi-way search tree, akin to the binary search tree property. This is the new case. So if case 1 doesn't happen, if there's a record at position I+1 in P, so you might ask, how do you figure out what this position is? So the natural thing is that you use get to find out where it is. So you search for it, and of course, when you know it's in a node, you can always use binary search to find its position, right? If you need to do that. But if it's not in the immediate right position, it might be further up the tree. So if that's the case, this is just like in the binary search tree, where what you do is you just follow the parents up the tree, and you find the smallest key that is larger than k. So rather than going into the details here, I'll just show it in an example, but also it's just like the one I gave you for binary search trees, this one case here. So anyways, let's do some examples. So suppose that I wanted to get the successor. Suppose I want to get the successor. Suppose this is R. So that's the root. Let's say if I want to get the successor of 14. Well, notice that in this case, I have this child, and this child. This is my immediate one that's associated with my position. So P.child is actually associated with the one where it's in that position for its key. So it's one thing to be helpful to be keeping that in the back of your mind when we're doing this, is that as soon as you find where it is, you just simply look at its immediate child, which would be that node's child. You look in there, and you compute smallest. So the thing here is that if I want to get smallest here, notice I'm just right here, right? That's just the first child. I go as far left as possible. It's right there. So that's just like case 1. So let's suppose we do the successor of 20. So I find where 20 is. So this would be the node that it would be in. Then I look, notice that my immediate child right here, you're going to get used to having to associate this child with this key. So they're all going to be paired up like this, if you think back to the way we represent it as a node. So I check this one, it's a leaf node, right? So I don't have anything there. So I check if the next position in my collection at that node. So I look in there and hey, look, I have a record right here, right? So that's the successor. This is like case 2. And suppose I do the successor of R13. Suppose I want to get the successor of 13. So what I could do is I find where 13 is. Notice that my immediate child is in fact a leaf node. So, and also I have no position to my right. So that means I'm going to work my way up the tree, figuring out if the successor is there. So you might ask, Dad, how do you do this? Well, one thing you can do is just do binary search and find the next largest spot that would have the one that's larger than K. So you can use binary search to achieve this, but you'll notice that here, this isn't quite right because look, 11 isn't bigger than 13. So I work my way up the tree. So notice every time if I did binary search to try to find the next largest key that's bigger than 13, notice that the index is always going to get me at one that's beyond it. So it means I'm going to go back up here. I keep working my way up the parents, and boom, there's 14 right there. Now, you might ask, okay, what about, let's do one more. So suppose I compute the successor of 42. So I find where 42 is, or what node it would be in. I work my way down here. Notice that my child that's associated with my key, it's a leaf. I have nothing to my right, so I go up to my immediate parent. I see if there is a record that's slightly big, it's just big enough, it's larger than 42. And in this case, I find it. It's right there. In this case, I find 50. So the question is, if I were to compute the time complexity of successor, notice it's just a combination of some of the operations we see last day. So if I wanted to compute the time complexity of this, is it okay if I erase my 4 examples here and I put the time complexity right here? Sure, let's do this. So I'm going to put the time complexity here. So how long does it take me to compute the successor? So first, that search that happens at the beginning, we know that this takes big O of h log d, right? That's what we established the other day. So that search takes big O of h log d. So this is me finding where the key k would be. Now, if case 1 happens, notice it computes smallest, which we established last day, is... question, what is the successor of 50? There is no successor. Yeah, so if you were to keep going up this tree, so notice there's nothing to the right, I would just check the immediate one to my right, there's nothing there. So I go up, notice that I will not find the position when I hit the root. So in this case, there would be no successor for 50. Okay, so if case 1 happens, we use smallest, right? And we established last day that takes big O of h. Smallest takes big O of H time. Now, here's the thing. If you find here's a little trick, is that if you find the position where it should be, you know already that position, so if you ever want to check the one immediately to your right, you already have that position. So in case 2, you could just simply do this in constant time. Case 2 takes big O of 1 time, constant time. And now you might ask, okay, what about case 3? So case 3 works its way up the tree, right? But every time I potentially have to do this binary search process to find if it's already in one of my immediate parents, if I work up the ancestors. Now, the height of this tree could be at most, it's big O of H, right? And each time I might do one of these searches. So that means I'm just going to combine these two things together. And case 3 takes big O of H log D time. Therefore, what is the worst case time complexity of the successor operation? So we know we have to always do this search. In the worst case, it's H log D. Each of these, I have H, I got a 1, and I got H log D. So what would it be? Yeah, it's big O of H log D. Very good. So that means that the time complexity is big O of H log D. So take note that if D is a constant, this collapses into just big O of H. So just keep that in mind. So far we talked about computing the successor. Now this was something that we implicitly did for our more complicated removals from our tree. So remember we had case 1 and case 2 for the binary search tree. So sometimes I have it where I'm going to have to do a removal, but the removal will not be as simple as just, hey, look, I get rid of it, right? I can't just simply do that every single time. I have to figure out what the successor is. So that brings me to removals, and I surprisingly don't have a whole lot to say about it. So we'll do some examples with removals so that you get an idea of how it would work. So one thing I do want to make note of is that when you do insertions and whatnot, remember every time when I introduced another record, I introduced another leaf node into the given node. Just keep in mind that each one of these is associated with the same position. If you were to look parallel across the two arrays, the same index would be used for both. So just keep that in mind. Sometimes it's helpful to have that intuition. So for removals, it's similar to doing this with the binary search tree. First, you find the record, you remove it, and replace it with the successor if you need to. So if you're in a situation where you can just simply get rid of it, then you can simply do that, just like case 1 in the removal of the binary search tree. However, it may be the case that both of my children might be internal nodes, where it might not be as straightforward to do the removal. So what are these trees called again? They're multi-way search trees. Multi-way search tree. So we're going to be specializing the concept of multi-way search tree in a little bit. So I thought we would do some examples of trying to apply this idea. So I have my tree over here. I've learned from last time not to redraw this. So that dastardly dad. So let's try doing some remove operations. Suppose I remove 42. So I find where that record would be, what key, I'm going to find its key. Notice it's right here. So notice right here that it has so notice that one, its immediate left and its immediate right, both of them are leaf nodes. In fact, at least one of them is a leaf node. So here's the great thing. I could just simply get rid of this. So I'm just going to take this node and I'm just going to get rid of it. Because I only have one record in it, so I can get rid of the whole node. And then I could just simply replace this with a leaf node. So that's how I could do the removal here, because it's safe for me to do so than just immediately just remove it. I don't have to compute the successor in this case. So next, let's try doing another removal. Next, let's do remove on 11. So notice here that if I look at trying to remove from 11 here, notice that if I do this, I'll find the appropriate spot where 11 is. It's right here. It has a leaf node here, and it has this internal node with some records in it. So naturally, if I want to find out what node I should be placing right here, are there any ideas what I should be doing? Any ideas at all? Yes. So yeah, you could do a couple of different things. One of the more standard ways to do this is just simply to just compute the successor, because notice that in this case, I have an internal node as one of my children. So I just get the successor and I just place it right here. So I'm just going to remove 11. I'm going to copy over the record. And then I'm going to get rid of that record right there. So I do the removal at where the both of the my adjacent children are leaves. Could you bring down the 10? I guess you could. Let's think about this. If 11 was right here and I get rid of this and I move this down, technically you could, but I want to make sure I do this in a consistent manner. Finding the successor, if ever it's really unclear how I do the removal, just get the successor, replace it there, because I have an internal node right here. And notice that in that internal node, I have at least one record, so I could just simply get the successor from here, just copy that into here, and then just do the removal. So it's not quite the exact same, but I must stress that you can keep doing this. So, if, for example, if I remove 13, notice that if I do this, notice that both of my immediate children are both leaf nodes. So I can just get rid of this right altogether. So we cannot bring the whole thing with 12, 13. Well, see, this is the thing, is that we're going to try to have it so that the successor algorithm is easy enough for us to use whenever it's unclear that I can replace a node. Because you're going to notice that once we start actually getting to some specific multi-way search trees, I usually don't want to destroy nodes. I usually don't want to make more nodes. So in this case, I'm just going to keep the same number of nodes. I'm just going to move the successor up into here. And since it exists, I'm just going to do that. If I didn't have a successor, you could... So notice if I had this, for example. If I had 12 right here, I could have, by principle, done the exact same thing. I could just compute the successor, grab this, copy it here, then delete this. So you're going to find that if needed, you're going to just find the successor, move it into the appropriate spot, then delete its data in that node, the one where it exists. You're going to notice that this is somewhat different than the one we had for the binary search trees, where we had it where we can always know that there's one child, at least that's a leaf. In this case, we want to be really cautious when we do this, because I have many records. So you might ask, Dad, what is this all about? So, like, what's the time complexity of doing this? So, of course, we have the search. So we search for the record. We search for the record with key K. We know how to do this in HLogD. Then, if I ever want to get the successor in this case, I could just simply apply smallest if I would like to. or I could just simply use this approach over here. So I'm just going to keep it simple to something akin to our binary search tree. So with key K, takes this. So let's see here. But the whole idea here is that when I do these removals, I'd like to get the immediate successor and replace it if possible. So I have the search, then I have it where if I want to get the successor, in this case, when I'm doing these removals, I can compute the smallest if I would like. This could be done in big O of H type. Now, if I do any removals of data, so removal of any data, and the deletion of possibly 2 nodes may happen. So when this happens, you can think of it in terms of the data structures, which all are of size big O of D. So I could do remove, so therefore, remove takes, here's our friend again, D plus H log D time. So it's plus right here. So if ever I could get the successor, that's what we're going to stick with. If I could get the successor, I'm just going to replace that with the successor like I did for case 2 of the binary search tree. If no such thing exists, which will be my immediate next node, if it doesn't exist, I just get rid of it. But the point is, now this is one thing that you might notice, is when I do these removals, you'll notice that the number of records that are in a node, it can shrink, right? It means that the order of that node, the number of children it has, could go down. Now, so one thing that we're going to have to reconcile is the fact that when I do these removals, there's a possibility that I might end up with a node that has no records in it. Now, we talked about how we just removed the node, right? But the thing is, what if that is actually allowing us to impose some special structure? So we're going to see how we're going to deal with these fat nodes and the nodes with very few records. Because if I could get those under control, I might be able to speed up a lot of these operations. So, before we proceed, are there any questions? Because we're going to talk about a specific kind of a multi-way search tree next. We're going to specialize all of this. So what's D again? Sure. Okay, so first we do the search, which that's H log D. Computing the smallest takes big O of H time. Now, notice that H is dominated by H times log D. And then I have any removals that may happen at a node, which may involve shuffling records around in a node, which can take big O of D time. So that's where the D comes from. The D is just simply this process of removing or maintaining the collections or secondary data structures at the nodes. So you just think of it as a linear process that's just going to do the shuffling of the elements so that they line up with the appropriate children. Or you could just simply think of it as, hey, look, if I delete a node, most certainly that will take some constant number of operations to do, but that's most likely going to get covered by big O of D. Hey, no worries, though. Wonderful question. So, when did we find the smallest for removal? Because when we do the removal, if I imagine I'm at a node. Imagine I'm at a node like this one. Notice that instead of having to, like wherever it's unclear where I do the removal, I can just simply use smallest to get the next key or record that should go right here. I can replace that there, then I can just delete it from this node. So the whole idea is that if I can find a successor to replace it, I will do that. One thing I do want to note is that when we start getting into the more technical data structures we're going to see today, most of these cases are going to be much simpler. So just to be very clear, even this is a lot flexible of a structure that even if you use the put and remove algorithms that I mentioned, they would not produce trees like this. Because remember, like I said last day, our put operation will just simply put it into another node. It will just increase the order of that node. It'll be a fat node. So I need to do something still to put this all together nicely. But multi-way search trees, and generally these are kind of the procedures for doing things, but we want to specialize them because notice that all of these are pretty similar to their binary search tree counterparts, but that's a feature. That's a feature of doing this. So you can, if you have the successor, you know it's right away down, right? You can just go down if it exists, but if it doesn't exist, you can just safely just remove it from the node. So just as an example, just to illustrate my point, is notice here that I have 1, 8, and 10. If I were to remove 8, notice that I can just remove this and it doesn't affect anything, right? Because the successor is not down here. So I could just go, I could just get rid of that right there. So notice that I don't need to compute the successor in this case. That's a wonderful question. Two there. It's okay. Notice that when I have a node that looks like this, with 2 leaf nodes like this, notice that if this happens, I'm going to have to potentially remove this node, and I might have to do something with this node. We're going to see that when we start manipulating these data structures, you're going to see that in our case, I have these 2 nodes right here. So you can think of it as this node and its immediate one right here. If I were to try to get rid of 13, I would just simply put this node right here. So I just delete these 2. So that's what the 2 means there. That's a wonderful question. Okay, so you might ask, Dan, why are you even showing you all this fun stuff? Well, I want to get to try to show you how we could use the multi-way search tree to represent other data structures that are larger families of search trees. So the first one I'm going to show you is the so-called 2-4 or 2-3-4 tree. And this data structure will resolve one of the major issues we had. It will deal with the whole issue with the fat nodes, and also what happens when I have no more records in a node. So those are 2. Those are 2. So just like when we studied the AVL tree, we're going to have a couple properties that we want to maintain at all stages of manipulating this data structure. So let's talk about 2-4 trees. So we have 2-4 trees. I must stress that sometimes these are called literally like 2-4 with a hyphen like this. And some people call it a 2-3-4 tree. In case you're ever finding yourself like, I want to go look into this. Sometimes people use different names for this one. So we're going to consider a particular kind of multi-way search tree that's going to have 2 properties. 2 properties. So then we're going to consider... So we will consider a multi-way search tree with 2 properties. So here are the 2 properties. So this is what defines the 2-4 tree. It's a multi-way search tree that has these 2 properties. It has the size property. So the size property just simply says that each internal node has at most 4 children. So that's what the size property says. That's all it is. So this will ensure that our nodes don't get too fat. So That's the first one. The other one is so-called the depth property. So this depth property is, by the way, going to make the tree have a simpler structure for our removals to be much easier to perform. So if you're wondering, okay, well, Dad, you did this thing. Okay, well, what do I do in this case, this case, this case? Removals are much simpler when we're going to have this depth property in place. So every leaf node has the same depth. So if you're wondering what the nodes of this tree will look like, you'll have it where, because of the size property, you're going to have possibly what we call a 2-node, right? A 2-node, we might have a 3-node, or possibly a 4-node. So just remember that the number of records that are in one of these nodes is always one less than the number of children it has. So these are the types of nodes that will be present in the 2-4 tree. So only these 3 kinds, if we're satisfying the properties that we have for the size property here. So you might ask, okay, so Dad, what would one of these 2-4 trees look like? So here's just an example. Let me just do a fun doodle of a 2-4 tree. So here's my root. I'm going to have 11, 21, and 28. Its first child is going to be an internal node with 5 and 7 as the keys. The next one will have just 18 in it. Next one will have just 23 in it. And let me just make a little bit more room for our friend, the 42. So I'm just going to put my leaf nodes in. So this is an example of a 2-4 tree. So notice that every one of the nodes is either a 2-node, a 3-node, or a 4-node. And it has the depth property. Notice that if I look at the depth of all of my leaf nodes, they have the exact same depth. Remember, depth is just the number of ancestors you have. So in this case, all of these have depth. There's 1 node, 2 nodes. So, question. What would be the order what would be the order of a node in the case of the 2-4 tree? Right, that's 4. So notice that 4 is a constant. So D is now a constant. So just keep that in the back of your mind, because all of our operations, we had a D in them. So that means that there's kind of 2 things. 1, I have D as a constant now. And 2, what exactly are we going to do with all these insertions and removals? We'll have to be a bit more careful with this. So all the algorithms we talked about, they're not much any different, really, at all. Just now, the difference is I would like to have it so it maintains these 2 properties at all times. Because notice that these are actually 2 strange things that happen with our multi-way search tree. 1, the internal nodes could potentially have a lot of children. Or it could be that the leaf nodes are just all over the place, making it a little bit more difficult to figure out how we're going to do removals. So, for example, what do I do with a node that has no records in it, for example? Or doesn't have enough records in it to find, say, a successor appropriately. So we're going to address both of these things, but I want to give you a claim, and we're going to prove it together. So here's the claim. Here's the claim. Any 2-4 tree, with n records, has height big O of log n. So my claim is that if you give me a multi-way search tree that satisfies these two properties, it will be the case that its height is always going to be big O of log n. So you remember all of our operations had most of them had h in it, right? And this is quite similar to what we had for the AVL tree, right? So is that interesting? Is that we can show that the 2-4 tree is going to have a logarithmic height? The proof for this is surprisingly simple. So let's prove it. Let's prove it together. So here's the trick with this proof. I'm going to try to make it so that the height is as big as possible. So to do this, remember the number of records is n. What I want to do is put as few records in a node as possible. Now, you might think of a type of tree data structure that has such a property. Can anybody think of a search tree that has as few records in each one of the nodes? So I'll give you a hint. It's highly related to the things we've talked about here. But think about it. Here I could have several records in a node. What I would like to do is make the height as big as I possibly can by putting as few records in a node as possible. Yeah, it's a binary search tree. Very good. Very good. So what I'm going to do is I'm going to bound the height based on these two properties and the fact that it resembles a binary search tree. So here's the idea. Very good observation there. So let h be the height of a 2-4 tree. Of a 2-4 tree with n items or records. Observe that every one of the internal nodes has to be at least a 2 node, right? That every internal node is at least a 2 node, right? We only have 3 kinds of nodes here. Is at least a 2 node. So we could just pull out our best friends from earlier, and we'll try to come up with a relationship we could get for the height. So let's see. Then T has at least to the power of I items at levels I is equal to 0, 1, 2, all the way up to h minus 1. But here's the thing. Here's the neat thing. If you look at the final level, the highest depth of all the nodes, what nodes are those? Are they internal nodes, or what kind of nodes are they? What kind of nodes are they? The ones at the deepest level of the tree. They're leaf nodes. Is that a wonderful observation? So let's just use that. And no items at level h by the depth property, right? So we're just using the depth property right here. So if I want to bound this carefully, I know that the number of records is going to be, it's going to definitely be bounded in this manner. So I look at each one of the levels. At most, it's going to look like this. 2 squared all the way up to the power of h minus 1. Which, if you notice, this is something that looks like a, what kind of series is this one? What does that look like? It's a geometric series. Very good. So if you use the geometric series here, so if you use the finite version of this, you'll end up with 2 to the power of h minus 1. But notice that I could just this simply means that I can take what I have here, and now I'm saying that n is greater or equal to 2 to the power of h minus 1, right? So let me just rewrite it like this. So I'm just going to take that minus 1, I'm going to put it on the same side as n. So I'm going to end up with 2 to the power of h is less than or equal to n plus 1. Now, are there any ideas what I could do next? Any ideas at all? We've seen an idea that's kind of like this before. Yeah, take logarithms to both sides. Perfect, everybody. Perfect, everybody. So all we're going to do is take logarithms to both sides. Taking logarithms to both sides. To both sides of the inequality. Both sides of the inequality. It follows that h is less than or equal to log base 2 of n plus 1, which this tells you right away that the height is at most log base 2 of n plus 1. Therefore, h is big O of log n. Boom, that's it. That's the whole proof. It's really simple. It's surprisingly simple of a proof. It relies on the two properties, our size property. We use that to determine what the shape or what our nodes look like. Then we use the depth property to bound how many nodes are possible at a given level of the tree. So you might ask, okay, what does that mean for us? What's the consequence of this claim? Since d is equal to 4 and h is big O of log n, so we can immediately see that searching takes big O of log n time. So that's the interesting consequence we get. That's at least one of them. We get a lot of results for free based on this neat little theorem, the M word, or mayonnaise. So are there any questions about my argument here, like the claim that we have here? It's kind of a cute proof. I mean, if you think about it compared to the one we did for the AVL tree, this one surprisingly, it seems even simpler, right? Which is, I think that's always kind of surprising given the fact that the tree looks a little bit more complicated. So remember, when you're proving claims like these, you can think about the properties that the tree has and use those. Those are usually your best friends. Look at these properties as things in your toolbox. So you might ask, okay, so we know how to do searches in big O of log n time, which is great. So keep in mind that the 2-4 tree is rather general, right? So it encapsulates, for example, the family of all binary search trees, right? So you might ask, okay, so how do we do insertions with our 2-4 tree? So let's talk about that. So I'm going to introduce you to more operations. Just like, you know, when we had for the AVL tree, how we had rotations. I'm going to introduce some more operations that I'll expect you to know. But are, I think, rather natural given the fact that we want to satisfy the size property and the depth property. They make a lot of sense when you put them in that context. So remember, at the end of the day, I would like to make sure that all of my nodes at the deepest level are all leaf nodes, and 2, that my nodes don't get overfilled. So I want to make sure I have both of these two things, but also if I do a removal, what happens if I have no more records in a node? What do I do to maintain the depth property where I have all the nodes at the same level, the leaf nodes? So the question is, what do we do with this? So let's talk about it. So let's talk about how we do insertions, how we can do the insertions. So let's talk about insertion. So here's the fun thing, is that we just do the insertion just like we did previously for the multi-way search tree. So we start off by just insert record KO as described for a multi-way search tree. So you start off by doing this. And you remember that when I did these insertions, we had this problem where it would just create a whole bunch of, it might create one really fat node. So I need some way to quell this because I can't have more children than a given 4 node, right? So we're going to be introducing a way to resolve this issue. So such an insertion. So if I just do this insertion, the big thing I want you to notice is it maintains the depth property, but it does not necessarily, it might violate the size property. Maintains the depth property, but may violate the size property. So what I mean by this is that it's possible for me to do these insertions and I end up getting a fat node, and instead of it being a 4 node, it becomes a 5 node. So what I mean by this, a 4 node becomes a 5 node, and this is the technical term for what happens, causing an overflow. So we refer to nodes that violate the size property as those that, like if I have it where it has more children than I'm allowed to have, we call that an overflow. Naturally, when I have very, very few records in a node, I'm going to have an underflow. We're going to focus on what happens when you have the overflow. Naturally, I think it's very easy to remember what overflow is. If you imagine it like I have my fat node, and say if I have my favorite pants, and I want to put my favorite pants on, but I'm overflowing from it. So, like a muffin top, for example, or something like that. So, that's one thing that helps me remember these, but hopefully you found that kind of fun. Anyways, so to fix the overflows, we do something called a split operation. So the split operation I'm going to define here, and then we're going to do some examples, okay? So to fix this, we perform a split operation. A split operation. So I'm going to define the split operation here for you. So I'm going to draw you a picture, and we're going to go through step by step. So I'm going to show you the steps of the split operation. To fix it, you gotta go to the gym. The split operation is getting me there, okay? Anyways, let's see what happens here. So suppose that I have a node that's up here. Just for the sake of simplicity here. And suppose that I get down to some node where I do the insertion. So I have 1, 2, 3, 4, 5 children. So I have C1, C2, C3, C4, and C5. I must stress that some of these might be internal nodes, but for the sake of drawing this picture for you, I'm just going to keep them as leaf nodes. The operation still works the same way. But remember, all the leaf nodes are at the same level, so it keeps things very simple with how the leaves operate. So anyways, so what's going to happen is when I have this causes an overflow, right? This is a 5 node. So what I do next is I'm going to consider the following. So I have K1, K2, K3, and K4. So what I'm going to do is I'm going to split right about the middle. If ever there's a tie that has to happen, we always go to the slight right of the middle. So if you think of the child being like this child right here as the middle, I'm just going to always take it so that it's the immediate right to that. So if I look at this, I want to take this part here and this part here. I want to turn these into, I want to do something with this because this is overflowing, right? So here's an idea. Here's an idea. What I'm going to do is I'm going to identify the key that's, or data record that is roughly about the middle. I'm going to call that V. Sorry. I'm going to call that V. And what I'm going to do is I'm going to move V up to U. Naturally, if U doesn't exist, you would have this node that would go up the tree. So next, what happens is it moves up. K3 would go here. The left of K3 would be, I'll call this V prime. And I'll call its immediate right. I'll call this V double prime. So I have K1, K2, and I have K4. So this would be, so this would be C1, C2, C3, C4, and C5. So the whole idea is that I move up about the middle, whatever the key is, I move it up to the parent, and as we do this process, what makes this really interesting as a data structure is that we're used to the trees going down from the root, right? Where the tree goes down, so we traverse down the tree from the root, we think of the tree upside down. One thing that I find fascinating, and I hope you will find it interesting, is that this tree actually doesn't grow downwards, it actually grows upwards. So very much like a flower does. So you can imagine it like as I put in records, what's going to happen is as they get overflowed, I'm going to split about the middle and I'll sprout a new node if there aren't any records there. And I split it into two smaller nodes. Notice that this node is a 3 node, that is a 2 node. So notice that these don't overflow. But, question. So would we split at K2 or is K3? Yeah, we pick K3. So we're going to pick always to the right of the smack dab middle in this. So we'll always pick just to the right. It's an excellent question. So, question. Is it possible for an overflow, an overflow to happen at this node? Remember, this is node U. Is it possible to happen? Yes. So what's going to happen is that it may have it where several split operations have to happen, and you work your way up the tree following up the parent. So this is what the split operation does. So I want to mention that multiple overflows may happen. So this is the split operation. So yes, so you may have to make it so there's a new root. Very good observation there. So you might ask, okay, so Dad, what exactly are we going to do? So I'm going to do an example showing you how this split operation works beyond just our definition here. So let's do an example. So one thing I really want to help you just emphasize is that it's going to grow up like a flower as insertions happen. So it's not going to be like where I go down and I go to a leaf node and I do the insertion there. What's going to happen is I do the insertion at that appropriate spot, but then I'm going to have these overflows that are going to effectively move keys or records up the tree, almost like a flower growing out of the ground. It's rather neat. This is, of course, because all the leaf nodes are at the same level. So instead of having to confront that, we just simply, we go upwards. So we're just going to grow the tree upwards. So that means that we might have to reassign what the root is. So let's do some examples. So let me draw out a tree. Actually, yeah, let's do this. 11, Actually, let me draw it a little bit lower so we can kind of play around with this, because I have a feeling it's going to go upwards. So let's bring it down a little bit. So I have 11, 21, 28. I have 5, 7. You might recognize this. It should be similar to the example I gave earlier. Similar. 23. Then I'm going to have, on the rightmost child, I'm going to have 29. Actually, not 29. Let's have 30. Let's have 30. Let's have 36 and 42. So, I have this 2-4 tree. I'm going to do an insertion. I'm going to insert 29 in here. I was getting a little ahead of myself. I'm going to insert 29. So I find the spot where it should be inserted. So I find the spot where the node for where it should be. So notice here that I go to my immediate right. I insert 29. So one thing I want you to notice is that every time I do this, I'm going to go downwards down the tree. So when I come down over here, what am I going to do? I'm going to put 29 into this node. So let me just change this up. So when I do this, I'm going to have 29, 30, 36, and 42. So you might ask, okay, so Dad, are we okay? Is there anything I have to do still? Is there anything that is a problem here? So I put 29 in where it should be, as per the multi-way search tree algorithm we had the other day. So remember, I put it into the lowest insertion spot. Remember, I would find the leaf that would be Z, and I would find its immediate parent to tell me where to go. So, not necessarily about, so it is indeed greater than 28, so we would go to this one, right? But the thing is this node okay? So let's see how many children it has. 1, 2, 3, 4, 5. This is a 5 node. This means that this overflows. So this is an overflow, right? That's a problem for us. We want to make sure it's still a 4 node. So I'm going to do the split operation. So now one thing, as mentioned before, if it is that the parent exists, then you know you could go immediately up to the parent, right? But if it doesn't exist, then you would make a new root node, as was discussed in the chat. So, like I said, this is going to grow upwards. So I want to show you how this happens. So, notice I'm just going to do this. Actually, let's do it this way. So I'm going to now take 36. 36 is going up over here, right? So I'm going to move V up to U. So this is U right now. That's the parent. So I move V up here. Then what happens? Then I place it as per the split operation. I will take this and break it into 2 nodes. I take that and I break it into 2 nodes. I'm going to have 28 right here. And then I am going to have 36. 28, 36. I have my 3 node, 29, 30. Then I would have my 2 node, 42. So that completes the split operation. Now, question, are we done yet? Are we done yet? No, right? This node here, node U, that overflows, right? So this overflows. So I'm going to do the split operation. So I do the split operation. I'm going to just simply do the following. Then we're going to bring 28 up. So this is what V is. I'm going to bring 28 up. 28's coming up. Notice that I don't have a parent, so I'm going to make a new root node for the tree. Then I'm going to split this down the middle, like this. So I have 36, 21, like this. Now, are we doing okay? Or do we have any more overflows? Any more overflowing? Any more muffin tops? So I think we're doing okay. We're doing okay. So this completes the insertion. So notice how the tree grows upwards like this. This is because we want to maintain the depth property. And at the same time, we want to make sure all these nodes we ensure that they don't get too fat. So are there any questions about the insertion? So I'm going to write out the pseudocode for put. One thing I will note is if you want to see more examples, I'm going to have more examples in the notes. So if you want to see more examples, I have, I think, a couple more examples in the notes. So let's write out the pseudocode for put. So let's head over here. Come back here, camera. Camera, come back. Come back. But yeah, I always like to think of the 2-4 tree just like it's growing like a flower. So like the flower is growing upwards. So let's write out the put operation. Now, I'm going to intentionally write this in a more general way. It makes it easier for us to discuss this a little later on for a different multi-way search tree. So, let's talk about the algorithm. So we have algorithm. We have put. It has the root, a key, and some data or value. So, as input, so it's root R. And we'll say root R of multi-way search tree T. And then we have record or data KO. And all this will do is just performs the insertion. So we just insert KO into T. That's all it's going to do. So it's not going to return anything. So, remember how I told you there was this technical term I was going to use? Remember that I know which node to use because I always find the lowest insertion node? So that's the one that I'm referring to here from last day. Find node where K would be at lowest insertion internal node V. So I'm just going to add it to this node. Now this is where we're going to do this process. Actually, it's quite, I like the observation that somebody made in the chat here about how we have a downward process, then we have this upward process. That should remind you a little bit of like when we had the AVL tree, just like was mentioned in the chat that when we use the up, we had that up process, the updating the heights. We're going to do something very similar to this, just instead, we're going to see if there's an overflow that happens. So we're just going to have a while loop. So while node V overflows. We're going to do the following. So if v is the root of t, then, so if that is indeed the case, then you're going to create, remember we create a new empty root node. And set as v's parent. So this is just a simple check just to make sure that if I have a new root node, I make sure I update this appropriately. In all other cases, so this is associated with the if, then what I have is the split operation. So split v around the middle record k prime, move data with k prime to v's parent, and update parent's children. Right? That's what we did for the split operation. Lastly, all I'm going to do is I'm going to update v to be the parent of v. And that ends the while loop. And that's everything. So let's think about how we'd compute the time complexity here. So the first thing is finding this we know how to do in h log d, right? So I'm just going to first just start off by just simply just doing all of these with h and d in place. So I have big O of h log d for finding. To add this to node v, it takes big O of d time. Now to do what I have right here, this is just simply updating appropriately the records in a node. So there might do some shuffles, or it might create a new node. So this is all bounded by big O of, so all of this is big O of d. And while, though, remember, I go up the tree from the lowest insertion point, right? So all of this depends on height h. So I have big O of hd. So if I put this all together, let's look at the time complexity here. So I have big O of h log d. I've got big O of d. I've got big O of hd. Right? So if I look at this, I have h log d, I have a d, and I have an hd. Now most certainly, if I just put h and I just have d here, this is the dominant term in this. So this would be big O of hd, but we know that d is equal to 4 and h is big O of log n, right? So I'm just going to plug those in. So that means that, well, that's a constant, right? And h is big O of log n. So that means that the worst case time complexity is big O of log n for the put operation. So are there any questions about how I derive this analysis? Any questions at all? Okay. So if we're doing okay with this, give me 2 thumbs up. 2 thumbs up. I want to talk about removals, so I've got to talk about 2 more operations, then we'll stop for today. So let's proceed over here. So let's talk about how we would do these removals, because that's a rather important part of this. Remember, there was this issue of having it where if we have the nodes get too little records in them, they might turn into a 1 node, for example. And it's not really clear that I could just simply delete the node. Because that would violate the depth property. So, let's talk about removals. So I'm going to talk about just the two operations today, and then we'll come back to this next time when I finish talking about these. How long extra are we going? I'm just defining two operations here, and then we're stopping for today. So that way we're going to talk about remove next class. So removals. So we just perform remove as before. As before. But a two-node may become a one-node, right? And that, of course, happens when you remove all the records from a node. So we cannot have one nodes in this tree, right? That's going to be a problem for us because that violates the size property, right? So a one node only has one child and no keys. No keys. It underflows. It underflows. So there's going to be two kinds of operations we can quickly do. One of them is going to be called the fusion operation. The other one is called the transfer operation. So the fusion operation, this is what we're going to do if we lack enough siblings that have enough keys. We're going to kind of combine them all into one node. If we have enough sibling records, so one in our immediate sibling, one of our sibling nodes, I can borrow one in an operation very similar to a rotation from an AVL tree. So the first one is that there's a... So to do this, we look at adjacent siblings. So the first one is the fusion operation. So we do the fusion operation if adjacent siblings of V are so if one record were removed from them, it would underflow. So this means a sibling of mine doesn't have enough records for me to borrow one. So I like to think of this like you're borrowing from your best friend. So if I have a sibling, or in fact, we can think of it as best friend, or say you have a family with brother or sister, and you have a sibling, and your sibling has some toys that you would like. So if they have enough toys to share, your parent might say, hey, look, you can have this toy, I'm going to share it with you. But if I don't have enough toys, we have to play together. So that's what a fusion operation will effectively do. So we fuse nodes together. So you're going to merge some nodes. So let me draw you a picture of what this would look like. So I have U here, and I'm going to have K and K prime. Now, these records may not exist, the ones with K and K prime, but I'm going to have one with K2 in it. So suppose that I have it where one of my nodes is now a one node. So this is, I'm going to call this W, I'll call this V. What I'm going to do is I'm going to perform, for a fusion operation, I'm going to combine K1 and K2. I'm going to take this middle key, I'm going to drive that into a new node, which actually our node here, I'm just going to shove both of these in. So K1 and K2, they're both going to go in here. So that I'll have enough records to call it it's not going to violate the size property, right? However, when I do this, this decreases the number of records in this node. So you have to be very careful about this. So fusion. So I have K, K prime. I have V. I have K1, K2. So I get a 3 node as a result. So all I have to do is I fuse together, I take this record, that record, I throw them both into V. So I fuse them together by merging them. So one thing to note is that underflows may happen at the parent. At the parent. So I'm just looking at the time here. I can either finish talking about the other operation or we can leave it for next time. Would everybody be okay with me either stopping here or talking about the other operation, which will only take me to about 2 minutes? It's just really one small picture that I have to draw. Okay, so I'll quickly just walk through this one, and then we'll stop for today so that we'll see how we can use these fusion and so-called transfer operations. But one thing I want to notice here is that suppose that I have a sibling and they have enough toys, but I need to make sure that I maintain the properties of the multi-way search tree. Just like if I had a binary search tree, I need to make sure that the keys are in the appropriate order. So we're going to do something quite similar. It will remind you eerily of the rotate operation. It will remind you a lot of it. At least my hope is that it'll look something somewhat familiar to you. So the other one is called the transfer operation. So there is a sibling W. A sibling W. We could borrow a record from. So what we're going to do is we're going to transfer over one of the keys so that I can bring it down to where the 1 node is so I can turn it into a 2 node. So here's the setup for how this will look. So I suppose I have K3 right here. Like I said before, these two might not exist. K and K prime may not exist. So in this case, I have a sibling called W that has enough keys that they could borrow one to my 1 node. Because I have 2 records in here, if I give one away, that's okay. So I have my 1 node right here, where I have the underflow happening. So all I do is the following. So what do we do to maintain the ordering? Well, look at this. Well, K2 is indeed less than K3, right? So that means that to maintain the ordering, what I could do is I could bring up K2 right here, and I could bring K3 down right here. So notice that I'm doing something that looks kind of like a rotation. It's not quite a rotation, but it's somewhat similar, right? So watch this. Transfer. So this is all the transfer we'll do. So if this is U, so I have U here, I have K, I'll have K2 right here, I'll have K prime. So I'll just have K1 right here. And then I have K3. So I introduce a new leaf node. So the idea is very simple. I brought up K2 here, then I brought down K3 into my 1 node. So I just hand it over. So just like that, yeah, exactly. It's like demoting. Very good, very good. So when we come back next time, we will see how we can use these to do removals for our 2-4 tree. Then after that, we're going to talk about our last data structure, which is the B tree. So I'll say thank you very much, and have yourself a beautiful evening. I'll see you later.